Okay, next up we have Ulrik Buchholtz, who's going to tell us about tangent bundles and Euler classes.
Okay, thank you very much. This is joint work with Dan Christensen, David S. Myers, and Egbert. And yeah, we are almost done with the paper, but it's still work in progress, and some things are still a little bit, we have a few things to formalize. So Dan is doing the bulk of the formalization in Coq, and we want to complete it, so it's not quite done. So here's what I'll tell you about. So I said tangent bundles and Euler classes. I'm going to do it in the other order. So we'll do some Euler classes first, and then we'll talk about the tangent sphere bundles on spheres. What we're not quite done with yet is the proof of the Whitney sum formula for Euler classes, but I'll tell you how far we've gotten so far. Okay, so some preliminaries also on this slide. For any type T, you have the classifying type of T bundles. So you have this B aught of T, which is the classifying type of the group of automorphisms of T, and a map into this type is a family of types, all of whose fibers are merely equivalent to T. And for the purpose of this work, let me say that a T bundle is oriented if instead of having a mere equivalence, you have a set truncated equivalence. So this works very well for families of spheres and families of Eilenberg-MacLane spaces for the integers that have Z mod 2 as the automorphism group. And then, so you have, when you set truncate, you have a choice of two different equivalences. So the set truncation of the equivalence of this n sphere with itself has two elements, a map of degree 1 and a map of degree -1. So we think of these as an orientation. And then with the same co-authors, we had a paper last year on central types. And so let me just recall the main results. So a pointed type is central if evaluation at the base point gives you an equivalence from the component, the connected component at the identity, to the type itself. So you always have this map, and if this map is an equivalence, we say that T is central. And the fact is that if you have a central type T, and you take such an oriented T type, so a type that's equivalent with a set truncated equivalence to T, then evaluation at the base point gives you an equivalence in the type B odd 1 of T. So if you have such a path, you can give an underlying equivalence, and you can evaluate that at the base point, and that gives you an equivalence to X. So if you put in the base point of B odd 1 of T, which is T itself with the truncation of the identity, then so if you put that in for X and omega, that tells you that B odd 1 of T is a delooping of T. So this gives you a delooping machine. So it's a slightly different, but some specialized way of producing deloopings, closely related to David's paper on Eilenberg-MacLane spaces as well. So Eilenberg-MacLane spaces are central, and they also have unique H-space structures, so they're two different but related ways of producing these deloopings. Okay. Right, so here's how to define the universal Euler class. So for the purpose, again, of this paper, let's define the nth delooping of the integers, which is the Eilenberg-MacLane space Knz, as this type of oriented Bn-1 sets, or Kn-1 sets. And we have the classifying type of n-dimensional sphere bundles, where I think of it as being, even though it's a family of n-1 spheres, I think of it as an n-dimensional thing, because I think of it as a remnant of an n-dimensional vector bundle where I take the unit sphere inside the vector space, or I puncture out the 0 element of the vector space, and I get something that's homotopy equivalent to an n-1 sphere. So I think of it as really an n-dimensional object, even though it's a family of n-1 dimensional spheres. And likewise, you have the oriented ones. Okay, so if you look at an oriented n-1 sphere, you can n-1 truncate it, and that gives you an oriented Bn-1 set. And that's the definition of, that's our definition of the Euler class. So if you have a map into BSGN, you also get a map to Bn set, so it's a degree n cohomology class. Okay, so what would you like to know about these Euler classes? Well, one thing is the Whitney sum formula. So you can take a direct sum of oriented sphere bundles, or just sphere bundles to begin with. So if we were thinking of these sphere bundles as the unit spheres inside a vector space, then the unit sphere inside a direct sum is the join of the unit spheres inside the factors. And there's a natural way, if you have an orientation of the summand, you get an orientation of the sum. I'm not writing that down here. And so the Whitney sum formula would say that this is compatible with cup products. So you can either take the Euler class of a direct sum or take the cup product of the Euler classes. Now this would be very easy to prove if we knew that the cup product in cohomology was induced via this equivalence on the left-hand slide, where BNZ is the oriented Bn minus 1 Z's. Because then if that was induced by truncating a join, then we would get this Whitney sum formula automatically. So the hard part is proving that this is a valid definition of cup products in integral cohomology. And note that there's a kind of funny level shift going on. So here we are truncating we have a sigma type of a type together with this orientation, and we can truncate the underlying type. And that's a level different than the usual definition of integral cohomology given by the truncation map, where you have the generator, which is the unit of the end truncation from the end sphere to its end truncation. And if you have that definition of integral cohomology, then you can do the cup products. You can induce that from smash products. So we want to know that this is all compatible. Okay, so here's a sketch of how this is going. So I mentioned we have these delooping machines, similar to what David wrote about. So in the same way, we could define cup products inductively by using this equivalence. So to give a bipointed map from Bn plus 1z and Bmz to Bn plus 1 plus m, well, by connectivity and truncatedness, such a map is equivalent from looping the first and the last type. And then so you can define, so there's a type, which should be a subscript, obviously a pointed type. So we can define cup products from n plus 1 m in terms of the one below by saying that it's delooping. And for the base case, we just use an induction on m. Okay, so we know that has to be the correct definition of cup products. Of course, when n and m are both 0, you take you have the bilinear product on the integers from the ring structure. Okay, so to prove that the local join, the truncated join definition is another correct definition of cup products, we have to show that it satisfies the same recursion equation as we do in the induction on n or on m. So in this step case in n, which is what I've illustrated, we need a pointed homotopy that fills this square here. And so this is really a homotopy of bipointed maps, but it suffices, since the final type is an H space, to just give an unpointed homotopy. So that's, I think we call this Evan's trick, so thanks, Evan. So let's fix, let's say, an argument in BMZ. And we need this outer square here to commute, where I've changed the right-hand side slightly. And the top square sort of commutes because both, well, for trivial reasons. And the bottom square then boils down to these equivalences. So it's a special case. Doesn't always hold that if you take a loop space on the left-hand side of a join, it usually has nothing to do with taking the loop space of the join, but it does in this case. And so we've done this, and what's left to do is to check the compatibility when x bar, so x bar is an oriented BNZ, so we have to check that that's compatible. So there's a little bit left to do, but I think we are pretty close to having the Whitney sum formula. Okay. The other thing we do to check that the definition of the Euler class is correct is to compare it with the Thom class, which was described in detail in Guillaume's thesis. So there's a universal space for the Thom class, which is the Thom space. You can do this for any oriented sphere bundle. So here we do it for the universal one. So the vertical map on the left is the universal oriented n-1 sphere bundle. And if you take this push out, that's the universal Thom space. And we want to define a cohomology class in degree n, and we call it the universal Thom class. And there's the zero section from the base into the nth universal Thom space. And we want to show that the Euler class is the restriction along the zero section of the universal Thom class. Okay. This is not so easy to do directly. We also want to compare it with Guillaume's definition. So Guillaume does the following. So there's a map of spans illustrated in this cube. So the back right square is the defining push-out square for the universal Thom space. And we can take this span instead, where the back left square is the sum of the defining push-out squares for the suspensions. So there are two different sigmas here. So the sum over the x bars, and then the suspension of the sphere. Okay. And now if we define Tn to be the push-out of this span in front, then you get an induced map. So it induces a commuting cube, and that means that the front right square is a push-out, and since one of the legs of this span is an equivalence, then we get an equivalence down there. Okay, so this is also in Guillaume's thesis. And so here's how Guillaume defined the Thom class. So pointed maps, so from this cube we get an equivalence. Pointed maps out of the Thom space, say to give a cohomology class, is the same as to give, for every oriented sphere, pointed map from the suspension to, could be any pointed type, but let's take BNZ. And here we can just take the adjunct of this map, which generates has a generator in BNZ, which is the loop space of Bn-1Z, which is a loop space of BNZ. On the right-hand side, there's a typo in the slide. I meant to say the following. I just meant to say that maps from a suspension are the same. So forget the sum. This should be now the product. Forget the product out here. Well, we could put a product. And then we do product over x, and then a sum over y, and then a map from x using the universal property of this suspension. And then the point in BNZ, which is the Bn-1 set with its canonical orientation. And again, you could do this for any pointed type. So this is what the slide meant to say. Okay. And over on the right, you can send an oriented sphere to, what do we have to give? We have to give the Euler class, and then we have to give this map, and we have a natural choice map there. And with this definition, so using the universal property of the suspension, this will automatically restrict along the zero section by construction to the Euler class. So this is the one where it's easy to check that you get the right Euler class from the zero section, and then we just have to check that it agrees with Guillaume's definition. But this is a proposition, and you can check it at the base point, and it's not that hard to do. Okay. All right, so now let's talk about how we construct tangent sphere bundles of spheres. This was also in David's HoTT talk. Let me go over it again. So for this definition, it's most convenient to use definition of spheres where they are joint powers of the zero sphere. So we define the n sphere to be the n+1 joint power of the zero sphere. And the zero sphere is, of course, in H space under multiplication. You can point it at +1. So the abstraction that makes the definition go through is to say that you have a reflection on a type, which is an equivalence, together with a homotopy from the identity join R to the symmetry on the join. So you have the symmetry equivalence for any two join factors A and B. A join B is equivalent to B join A. And so this reflection has to do this. So there's an intuition here over on the right. So if you take S0, this has to have such a reflection, and it's given by multiplication by -1, so swaps plus and -1. And we want to know that on the circle, taking the reflection, let's see, the identity join -1 is the same as the symmetry. And those are just two different rotations on the circle. Okay? And there's also a definition of what is a coherent reflection, and the one on the circle is coherent. This is there might be more conditions you could put on, but this is so for what I'm going to tell you later, this is what we need. Okay. So what we want to do is we want to define these tangent sphere bundles. So since Sn is an n+1 fold join power, I'm calling this tau n+1. So that's to be a family of n-1 spheres, together with some equivalences, saying that, let's see, maybe draw this. If you have a sphere and you have a point, so a point x, and then it has an orthogonal complement, a great circle, a great sphere, and if you take S0 join tau, let's say this is the n-dimensional one, then you get n+1 Sn. So if you take the direct sum of this line with this orthogonal plane, you should get the whole space. Okay, so we do this we define both of these by induction, and because we also want to do tangents on projective space, and we're actually hoping to have the attaching maps of some Grassmannians, we're generalizing this a bit. So here's the definition. We say an A torsor for any type A is just a type with a map like this. So if you have any type E, and if you have a point in E, you get an equivalence to A. It's a little bit non-standard, but it works very nicely for this purpose. If you swap the arguments and then you can take any join power of E, you get these scalar multiplication maps. So that's all we need this torsor structure for, basically. Okay, so the construction works if A has a reflection. It doesn't have to be coherent just for the construction itself. So the construction says that for any natural number and any point in the nth join power, you have this tangent bundle that's going to be merely equivalent to a join power 1 less, and you get an equivalence, this theta n. So for n equals to 0, there's nothing to do. Otherwise, you induct on n, and so we picture this as follows. So you have your E, and you have an E join n. So if you have an E here, then the orthogonal tangent bundle is just the E join n that's orthogonal to it. If you have an X over here, then then the tangents to such an X is take the tangents inside this this plane. So this is tau n of X, and then you join on a copy of E. Okay. And so how do you do the glue? So this now defines, okay, what is the tangent for E, this thing. What's the tangent for X? Well, it's this plane. And how are you supposed to join them on a glue from E to X in the join? And so what we want is you're taking these tangents and you want to rotate them like this. So what you want to do is you want to reflect x. So you want to take, actually, so to mix things out nicely, take r to the -1 of on the a factor, and then take the scalar multiple of e on that. So that's the thing that makes it work. So on the point constructors, so that gives you the definition of tau. But then to check that everything works, you have to have the theta as well. And this is where it's important that you think geometrically and you get the right definition. So use scalar multiplication in the left case. You need a twist and this in the theta case on the right case. And then so the glue case, if you go around, so let's see, twist and ID times theta, that's the in right case here. And on the bottom, we have T join the identity. And then I've changed the direction for what we have to compare it to because it's easier to get the commuting diagram in this direction. And then ID, if you associate this, you have an ID join and R, but that's the same thing as a symmetry, which is the same thing as twist. So if you take symmetry, join, identity, that's the same thing as twisting the first two factors. And then the top square is a naturality square, and the other square is an identity, so it works out. Okay. In the abstract, I gave a proof of the Harry-Ball theorem. So for the Harry-Ball theorem, we need this coherence condition, which gives us some paths saying that what this theta does on an in-left, that is the scalar multiplication. And then you can just compute, because inside the join, you now have paths from in-left 1 to in-left -1. If you have a point, you can just go glue and then glue from -1 to 1. So you get this homotopy from the identity to the antipodal map, and that gives you the Harry-Ball theorem. Okay, well, let's see that Eric is standing up, so I'll stop here. Thank you.
Questions? Okay.
Maybe B doesn't work. Is there a key that does this? That doesn't work.
Oh boy. Yeah. Any questions? Okay, I have questions.
Okay. You ask a question.
This join formula for the cup product, does it work more generally?
Yeah, you can do it for any ring. Yeah.
For any ring, that's what I was going to
Yeah,
say.
yeah.
I was asking if you needed any. I was wondering if you need any condition on the ring.
No.
Just the map is sufficient. Right.
Yeah.
That's what I was expecting. I was just curious. Do I have any other questions? Does anyone?
But
else
I mean, that's what I think. We haven't done. We're in the process of formalizing.
What's the missing thing? Is it just messy algebra?
Yeah. So you have to have some. There's some initial cases in the bottom range, because this join formula only kicks in starting at 2.
Right.
So you have some base cases to match up.
Okay.
And then there's one pointedness in the step case that is not done yet.
Okay. Yeah.
You've defined a cohomology class. You have the Euler class. Can you say anything else about generalized cohomology in general, or like, do you have more of the cohomology theory here?
Oh yeah, so we've done. I mean, there's lots of ordinary cohomology theories that's been done. And if you want more general cohomology, then actually, so the next thing I want to think about is to have a sphere spectrum version of the Euler class and compare that with this one, because there this truncation trick is not going to work exactly the same. So it'd be nice to compare that case. Yeah.
Oh, okay. Tom.
Yeah.
Yeah, so Ali is asking, how do tangent sphere bundles correspond to the usual tangent bundles in algebraic topology?
Yeah, so that's a good question. So I think if you work in, say, real cohesion, something like that, you could compare and get a sanity check that if you take the shape of the usual sphere bundles, which you could define there, you would get these ones. Yeah, we haven't done that, but it's a really nice project.
Okay, let's thank our speaker and go get some lunch. What do you say?